Okay, equilibrium. Banana. 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 Hey, banana. B-A-N-A-N-A-S. All right. Are we ready? Equilibrium. Super important concept. Everything we're learning, we're building for the next 3 units, leading up to solution equilibrium and what I call invader problems, which are tough. It's probably the hardest kinds of calculations that you'll be doing not probably. They are the hardest, most complex problems you'll be doing in this class. We got a while. We got unit 10 and then unit 11. 11 is the big one. So this is going to be a base that is really, really important. So please, if you have questions or you feel like you have holes in your knowledge, we got to get them filled now before we move on to when it gets real. So in general equilibrium, we just showed you the little demo where we had a reversible reaction. And in equilibrium, with that term equal comes from the fact that the rates of the reaction are equal, not the amounts. We can have different concentrations of reactants and products, but the rate of exchange is equal. So when we get to the point where we don't see a change in concentration in either of these of a reversible reaction, that's the point we reach equilibrium. So what we use to talk about what type of equilibrium we are, what's favored, what's not favored, we need to be able to calculate the equilibrium constant. And that is shown here 3 different ways. If you see K or K sub C, those are the same thing. That is the concentration of your products raised to the coefficient in the balanced equation divided by the concentration of reactants. It has to be concentration in molarity. You can also solve for Kp, which is just for gaseous systems only. And you have to be careful here when you write your K expressions. You have to use parentheses. If you use brackets on your expression, they're going to pop you one because that stands for molarity. And I've graded questions where if students used for Kp brackets, they didn't get the point for the equilibrium expression. And when I'm saying expression, I mean the unsubstituted equation. And that's always going to be the first point in any of those equilibrium problems you're going to get on the AP. Sometimes it's even a separate question. They'll say, write the equilibrium expression in part A, and then in part B, they'll give you a bunch of stuff, and you're supposed to either solve for K or solve for one of the concentrations. So it's a very common question, and even if they don't ask for it, you can still earn a point for doing it. So make sure you always do your expression. When you're writing expressions, you only include gases and aqueous solutions. We don't include solids or liquids in the expressions because do solids and liquids have concentrations, pure liquids and pure solids? No, they don't. Only solutions, and gas is basically a solution when you have gas mixed with other gases. So you only include aqueous and gases. And also, liquids and solids don't contribute to pressure changes. You can change pressure a lot, and nothing about the liquid or solid will change. Volume doesn't change, or just volume. Volume doesn't change when you change the pressures. So only aqueous and gases are included in these, and in KPs, it's only gases, period, that we're dealing with. Okay? Now, what does this number mean? There's 3 different things we look at, and it's all in this text here, but I just want to talk about if our K is greater than 1, it means something. If it's less than 1, it means something. And if K is equal to 1, it means something. Remembering that K is products over reactants is the key. If your K is greater than 1, what does that mean? There's more products than reactants. So it means the forward reaction is favored. We make more products than reactants. We're still at equilibrium, but that concentration on the product side is going to be higher. So more products, forward favored. Forward reaction is favored. If your K is less than 1, what do we have? More reactants. So that means the reverse reaction. We have more reactants. Reverse reaction is favored. Again, we're at equilibrium in both of these. They're equilibrium. It's just you have one more than the other. Turn to the back. Reactants is on the left, products is on the right. What's the magnitude of K of that thing we did in class just a few minutes ago? Less than 1, because we have more products than reactants. Weren't we at equilibrium? Right? But there were more reactants, sorry. So that means that in that case, K is less than 1. What about K is equal to 1? They're the same. And I'm glad I didn't hear it. Last period I heard someone yell, they're at equilibrium. Well, they're all at equilibrium. This just means, what would that mean for those buckets back there? Our levels would have been equal to each other the whole time. Okay? So this is, neither is favored. We have the same concentration of products as we do reactants. So the first kind of problem we're going to do is just a simple Chem 1 thing. And even in Chem 1 regular, I think they wrote expressions and just plugged in equilibrium concentrations. So you're asked here, calculate the Kc. So the first thing we're going to do is write the equilibrium expression. I'm going to want to see that. So your Kc is equal to products. These are all gases, so everything's going to be included. Hi, what do I do to Hi? Square it, divided by H2 to the first and I2 to the first. That is my equilibrium expression. That's going to earn you a point on the AP. Now, if you notice, see how all the concentrations they gave us have a subscript of EQ? They're telling you those are the concentrations once equilibrium is established. It would be the concentration of the buckets in the back right now, not the concentrations from before. It has to be when they're at equilibrium. So today we're giving you those because we're nice. Tomorrow we're going to be giving you initial concentrations, and you have to figure out the equilibrium concentrations in order to solve. So let's just plug in what we're given into the appropriate place. This is 0.30 moles per liter. H2 is 0.012 to the first. Oh, I forgot to square. I got to square my 0.30. And 0.15 here to the first. So to 2 sig figs, what is my answer? Calculators. I'll give you this one since you guys are slow, but get your calculators out. The answer is 50 with 2 sig figs. Now I finally have some good news. The good news being that you are not required to have units on any equilibrium K. Kc, Kp, Ka, Kb, when we get to it, Ksp. All these different Ks we have do not need units. It's truly only the equilibrium constant K that we need units on. Okay? Okay? Get it? All right, let's go to the next. Now, what I need you to be able to do, and this is all kind of an explanation. I don't want you to like freak out about it. This is just FYI. I'm going to teach you how to do this outside of this explanation. But there is a relationship to from Kp to Kc, the actual equilibrium constants. And you need to be able to convert back and forth. This equation used to be on the AP sheet, and it's not anymore. But it's definitely worth spending a little bit of time on. And I'll explain, how much of it you need to know for the AP. But the equation is based on Pervnert. If I were to divide both sides by volume, I would get P is equal to N over V times RT. Do you see how there's a relation between pressure and what's this? What's moles over volume? Moles divided by liters. Isn't that concentration? So do you see there's a factor difference between pressure and concentration? But they are related. So there is a developed equation that says Kp is equal to Kc times RT to the delta N. We call this the politically correct equation. I always had a hard time remembering, is it Kc is equal to Kp, or is it Kp? Politically correct. See it? All right. So we can plug whatever we need to find one or the other, Kp or Kc. This delta N, what is that? This is the change in moles of gas only. Because in order to have a KP, it has to be a fully gaseous system. So, change in moles of gas. So to find delta, it's always final minus initial moles of gas. And that's going to be the exponent based on the coefficients in the equation. And I'm going to show you how to use this momentarily. Okay, let's do a problem with it. Right here, the SO3 needs to be a gas. All right, so they give us the Kp, and they tell us to calculate K. If you don't see a subscript, it means Kc. So we're going to be finding Kc. So we're going to use the politically correct to the delta N equation. Okay. So Kp is 0.25. We're solving for Kc. Let's talk about R. Are we going to use the energy R or the gas R? Gas, because we're talking about Kp, pressure, right? So 0.0821 lattimolk times it's 1100 Kelvin in the problem. Now, delta N, raised to the delta N. Final minus initial gas moles. How many moles of gas are product, final? 2. How many moles of gas are initial? 3. So it's going to be raised to the -1. So everyone go ahead and solve for Kc and give me 2 sig figs. I got a bunch of answers in first period. I was like hoping, so I want to hear what y'all get. Two. 23, yeah, that sounds like what they got. So our Kc then is 23. So what's favored in this, products or reactants? Products. If it's greater than 1, more products. Forward reaction is favored. Now, are they ever going to have you really do this calculation on the AP? No, probably not. But here's what they can do. They can still ask you the relationship, but dollars to donuts, they're going to do it, and they're going to make this delta N be 0. If they make delta N 0, do you have any math you have to do? Because what does delta N being 0 mean? Right, but what does it mean? Kp is equal to Kc. I want you to conceptually understand that. If there is no change of moles of gases, if you have 2 and 2 or 3 and 3 in the equation, the Kp is equal to the Kc. So I could see them giving you that, because that conceptually is something you can understand. So know that if delta N is equal to 0, Kp is equal to Kc. So knowing just that alone, and you can reference the equation and say, since there's no change of moles of gases, Kp is equal to Kc, and you're done. So that's how I think they're going to test you on it, if it comes up. Okay, what else can we do with these Ks? We're going to manipulate these Ks just like we did in thermo, but we're going to treat them a little bit differently. If we have a reaction and we know it's K, we can manipulate that reaction and get a different K by watching the math. So for instance, we've already done this one. This was the first problem we did. There was our expression, and our answer was 50, right? So the question might be, well, what is the K of this reaction then? So there is a relationship between these two things. What's the difference? Yeah, isn't the reaction just reversed? So if this is products over reactants and we reverse the reaction, didn't the reactants become products and products become reactants? So what do? Reciprocal. So if you reverse the reaction, you take the reciprocal to find the K. You take the reciprocal of the original K to find the new K. What did we do in thermo if we reversed the reaction? We just changed the sign, right? From negative to positive or positive to negative. Exo became endo, vice versa. So we're doing the same thing, but it's a different mathematical application. Okay, this one's cool. What about this one? What did we do to this one? Or I should go this way. What did we do to get this? Divide by 2, and I'm going to play devil's advocate. We're really multiplying by what? 1/2. Remembering that coefficients are really exponents, right, in the expression, what you do is you raise the k to whatever exponent that you're multiplying by. So if you're multiplying by 1/2, you raise it to 1/2. If you're multiplying by 5, you raise it to 5. Since we multiplied by 1/2, we're going to take our original k and raise it to the 1/2, which happens to be the square root, right? So the square root of 50 is 7.1. So if you reverse the reaction, you do the reciprocal of the k. If you multiply through by something, you raise it to that power. Whoa. All right. Last type of manipulation is adding equations. When you add equations, you multiply their k's. And I'm going to show you just so you can see how it works. If we have a going to b, does everyone agree that the expression would be b over a, right? If we have c going to d, do we agree that it's d over c? All right, if I were to add these two equations up, we'd get a plus c equals b plus d. The expression from here, I'd write bd over ac, correct? So now look at this. How do I get this from this and this? Multiply the k's. So if you're adding the equations, you don't add the k's, you multiply the k's. So those are the three: reverse, reciprocal. Multiply through by a coefficient, raise it to that power, and if you add the equations, you multiply the k's. So here's a typical kind of very similar to, it is Hess's law sort of, flippy thing. We're just using k's instead. So equilibrium constants are given for those two reactions, and they want you to calculate k for this, our new goal equation. This is our goal. So looking at the first equation, how would that be useful? What does it have that we need? I see H2 and H2O, right? But what's wrong? Yeah, they're on the other side, so I should probably flip that first one. So I'm going to flip the first equation. I'm going to get CO plus H2O gives me H2 plus COO. Since I reverse the equation, what do I do to the K? Reciprocal. 1 over 67 is now the K of that reaction. And I do this just like I did Hess's law. Looking at this next one, what do you want me to do with it? I see CO and CO2. What do you think? Leave it. I'm going to leave it alone. So I get COO plus CO is in equilibrium with CO plus CO2. Since I left that alone, I'm going to leave my K alone. Now before I multiply those constants, I need to make sure I'm getting my goal equation. So what can cancel? COO and CO. And that leaves me H2O plus CO, whoops, gives me H2 plus CO2. Since that is the goal, it looks like it matches, I'm going to multiply my K's, and I'm going to get 490 divided by 67. So to 2 sig figs, what is that? It really doesn't say if it's K or KP, but oh, it has to be K. Oh, maybe not. What is it? 7.3. That sounds right to me. Does that make sense? Pretty easy? All right, last problem, because today is so tough. Calculate Kc for this reaction if we know the reaction for this, the K for that is 1.3E4. So we're starting here and we're going to there. That's what we're looking for the K for, up here. So what did I do to this equation to get this equation? I multiplied by 2. So if I multiply by 2, what does that mean for my K? I square it. And that is all. And what is that answer to 2 sig figs? 1.7 times 10 to the 8th. And that is the KC. Any questions? All right, so tomorrow we're going to start and use some rice tables. They're amazing. This class would be so much harder without rice tables. Like, you got to appreciate the beauty of the rice table. I promise I will buy this class donuts if you feel honestly that they're just as bad this year as they were last year. What? Something about donuts. What do you say? Anyway, I'm going to let these people at home go. Have a good day.